This is very common in recent year paper. This is very important in point of JEE Mains. This is the summary of zero and first order reactions. These are some useful conversions which will be helping in the entire physical chemistry. Hello everyone, I am Ashlin, second year student at NIT Calicut. In this video, we'll be quickly revising the entire physical chemistry in just 45 minutes. Without further ado, let's start with the first chapter, mole concept. 1 dozen, you know it is 12. Similarly, 1 mole of something is Na of that. Na in the sense it is Avogadro number 6.022 into 10 to the power 23. And so when you have some number of particles and you divide it with the Avogadro number, you will be getting the number of moles. Even based on this, you can get a question like this. There is a silver coating of 0.05 thickness over the plate of area this much. We have to find the number of silver atom. We have been given with the atomic mass and density. So first of all, we will be finding the volume, and from the volume we will be getting the mass, because from density you can find the mass, and from the mass you will be finding the moles by dividing with the atomic mass, that is the molar mass, and from the moles you will get the number of particles by multiplying with the Avogadro number. So simple, but still this is tested, so make sure you do this. Then these are some definitions which you can look forward, and if you have some confusions you can take a pass and note this. Then there are multiple ways you can find the number of moles. The first is using the weight. When you divide the given weight by the molar mass, you will get the number of moles. The next one is in terms of volume. Volume divided by 22.4 will give you the number of moles, and the obvious one, number of particles divided by the Avogadro number, will also give you the number of moles. This is a question based on these concepts, so take a pass, solve this and move ahead. These are some useful conversions which will be helping in the entire physical chemistry. Next topic is empirical formulas. In empirical formulas, you will be given with the percentages. Here you have 42.1% of carbon, 6.4% of hydrogen, and 51.5% of oxygen. Now we have to find the molecular formula such that the molecular weight is 342 grams, and first step is to divide it with the molar mass. That is, when you divide 42.1 using the carbon ka molar mass, carbon's molar mass is 12, hydrogen is 1, oxygen is 16. So when you divide that, we will be getting this 3.5, 6.4 and 3.2. Next, what you will be doing is you will be dividing these numbers using the lowest number, that is 3.2. When you divide, you will get a number like this. For carbon, it is 1.09, hydrogen 2 and oxygen 1. So you can write the empirical formula as C 1.09, hydrogen 2 and oxygen 1. Now from this we have to deduce it, because regularly when you multiply with N, you will be getting in value. You will be getting the value directly. Here, if you are multiplying with N equal to, let's say, 11, you will get C11, H22 and O11. But when you check the option, there is nothing like that. So you have to approach this in a little different manner. Like from the empirical formula, from the integer values, you can get that number of hydrogen is twice the number of oxygen. So when you check out option A, it is not that case, and when you check out option B, it is not that case. And in option C and D, you can see hydrogen is twice the oxygen. But one more condition which has to be satisfied is the molecular weight is 342. When you check for option C and D, you will find that option D is out of the race. So the option C is the right option. Check its molecular weight. So from that you will get the option C as the right option for this question. This is the approach to find the molecular formulas if the percentages are given. Moving on, we have the concept of limiting reagent. Here we have been given with the equation N2 plus 3H2 is given to NH3, and the nitrogen there is 20 grams and hydrogen there are 5 grams. We have to find the limiting reagent and the number of moles of NH3 formed. First of all, we have to find the number of moles dividing by the molar mass, 20 divided by 28 and 5 divided by 2. And now we will be dividing with the stoichiometric coefficient, that is nitrogen divided by 1, hydrogen divided by 3, and you will get this. Now we have to compare which is more. The least one is the limiting reagent. Here nitrogen is the limiting reagent. The concept of limiting reagent over here is you have excess hydrogen, but there is a limit in nitrogen. So entire hydrogen is not going to convert into NH3. So what we'll be comparing is we'll be comparing N2 and NH3. So based on the given relation, that is 1 mole of N2 is giving 2 moles of NH3, we are now supposed to find the number of moles of NH3. So we can say that 20.28 is the mole of nitrogen that is given. So twice that will be the moles of NH3, that is 2 into 20 divided by 28, which is 1.42 moles of NH3. That is the answer. The next one is combustion reaction based questions, and this is very common nowadays, and you can see the questions over here. We'll solve one question. The number of moles of methane required to produce 11 grams of CO2 after combustion. So here we have a combustion reaction, and you can see that 1 mole of CH4, that is methane, is giving you 1 mole of carbon dioxide. And they are giving us that we have to produce 11 grams of carbon dioxide. To produce 11 grams of carbon dioxide, that is 11 divided by 45 moles of carbon dioxide, you can see that we need 11 divided by 44 moles of methane, that is 0.25 moles of methane. So simple. Similarly, you can solve this question also. This is a photosynthesis reaction based question. The same thing, same unitary method will work here also, so make sure you solve this. The next one is concentration terms, and this we'll be looking in the next chapter, solutions and its colligative properties. The first topic in this chapter is concentration terms. The three important concentration terms are molarity, molality, and mole fraction. Molarity is number of moles of solute divided by the volume of solution in liter, mind the units, okay? And molality, denoted by small m, is the moles of solute divided by the weight of the solvent in kilograms. And mole fraction, let's say you have three different solvents in the solution, A, B, and C. You are finding the mole fraction of A. So it is moles of A divided by the moles of A plus B plus C. Simple. And the next is temperature dependent and temperature independent. This is very important in point of JEE Mains. Temperature dependent properties are which depends on the volume. Volume changes with temperature, so the properties which depend on the volume changes with temperature. You can note molarity, normality, strength, percentage weight by volume, percentage volume by volume are temperature dependent, and molality, mole fraction, and percentage weight by weight is temperature independent. Next one is Henry's law, which states that solubility of gas in liquid is directly proportional to the partial pressure of the gas present above the surface of solution. Henry's law is about gas and liquid solutions, mind that. Raoult's law is liquid and liquid solutions. This Henry's law, when you put it in terms of mathematical form, which is P equal to KH into X. X is the mole fraction of gas present in the solution. P is the partial pressure of gas present above the solution, and KH is the Henry's law constant. Raoult's law, as I said, it is liquid and liquid solution. Let's say there are two liquids which is combining to give you a solution, and now we are finding the partial pressure of the liquid above it. These are all volatile liquids, so it will be converting into vapors, and the pressure of those vapors is what we are finding. The pressure of the pure solvent A is P naught A and solution B is P naught B. When we combine it and write it, we will be getting that P total is equal to PA plus PB, and PA is equal to P naught A XA plus P naught B XP. And when you plot the graph between the vapor pressure along with the mole fractions, you will get a graph something like this. Earlier cases, we were seeing the mole fraction in the solution. If the mole fraction of A and B in the vapor state is given, you have to use this formula to get the total vapor pressure. Next one is ideal versus non-ideal solution. Ideal solutions are solutions which obey Raoult's law. Non-ideal solutions are which does not follow Raoult's law. In non-ideal case, there are two cases, that is positive and negative deviation. Positive deviation is a case where you find the total pressure is more than the ideal case, and in negative the total pressure is less than the ideal case. When you plot a graph, you will be getting like this. I hope you can see that this is the regular ideal case, and in positive deviation it is above, and in negative deviation it is below. And this examples the commonly tested in JEE Mains. So I would suggest you to take a pause and note all these examples and move ahead, because these are very important. Next topic is colligative properties. There are 4 colligative properties, and the first one is relative lowering of vapor pressure. This happens when you have a solution containing a non-volatile solute. Non-volatile solute in the sense it does not convert to vapor. So what happens? This hinders the solution to getting into the vapor state. So the vapor pressure is lowered, and the vapor pressure of the solution is less than the pure solvent. So we'll see that the lowering, that is delta P, is equal to pressure of the pure A minus the P of S. So P dot A minus PS gives the lowering, and the relative lowering, when you calculate, you will be getting it as the mole fraction of B, that is mole fraction of the solute. The next is elevation and boiling point. Experimentally, we find that the elevation and boiling point is directly proportional to the molality, not molarity, mind you, it is molality. So KB is the boiling point elevation constant, which you will be using it to remove the proportionality over here. Similarly, when it comes to freezing point, depression in freezing point, we find it experimentally, delta T is directly proportional to molality, and here the constant is Kf, that is freezing point depression constant. There it was Kb, here it is Kf. And the last colligative property is osmotic pressure, and osmotic pressure pi is equal to CRT. C is molarity. Now there's a case where abnormality occurs, that is, let's say you have an atom, it is dissociating into two, or there are two atoms and it is associating into two. Because colligative properties are properties that depend on the number of molecules. It does not depend on the nature, it depends on the number. So when association and dissociation happens, there is some abnormality occurs. So to remove the error, we multiply I. I is the Van Hoff factor for non-electrolyte. Non-electrolyte in the sense it does not decompose or it does not get associated. I is equal to 1. You need not multiply it. But for an electrolyte, I can be less than 1 if it is association. I can be greater than 1 if it is an dissociation case. And these are the corrected colligative properties. In every colligative property, you will be multiplying it with the I, that is Van Hoff factor. This is the case of dissociation, and degree of dissociation is alpha, and this is the case of association. I hope this was a quick revision of solutions. Now we'll be moving to the next chapter, atomic structure. The first chapter in atomic structure is Planck's quantum theory. This theory states that energy is not continuous, but it is emitted or absorbed in discrete packets called quanta. And this energy, the value of this energy of one photon is given by hc by lambda. H is the Planck's constant, which is 6.626 into 10 to the power minus 34 joule second. C is the speed of light, that is 3 into 10 to the power 8 meter per second. And lambda is the wavelength. And you can have the relation between frequency and lambda as C is equal to frequency into lambda. And also mind that energy hc by lambda is in joules. And when you are given with the value of the wavelength of the light in Armstrongs, you can use that formula 12,400 divided by lambda in Armstrong to get the energy in EV. Also note that 1 Armstrong is equal to 10 to the power minus 10 meters. This will help in few questions in JEE Mains. The next topic is photoelectric effect. In this, you have a light shining on a metal with a work function phi and the light having energy h into mu. And the electrons are released with the kinetic energy Ke. The relation is h nu is equal to phi plus Ke. The next topic is Bohr's atomic model, and it is one of the important topic of this chapter, and it is valid only for single electron species like hydrogen, helium plus and lithium 2 plus. According to it, angular momentum is quantized, that is MVR, mass of the electron, velocity of the electron and the radius of the orbit is equal to nh by 2 pi. It is in discrete quantities, it is not continuous and it is quantized. N is the orbit number, h by 2 pi is also constant. H is Planck's constant. And there are various relations which you have to know in this. First is radius. Radius is directly proportional to n square by z. Velocity is directly proportional to z by n. Energy of an electron revolving in an orbit is directly proportional to z square by n square. And there is a relation between total energy, kinetic energy and potential energy. Total energy is equal to minus of kinetic energy is equal to half of the potential energy. Over here, Z is the atomic number, N is the orbit number. With these, many JEE Main questions have been asked, so make sure you note this and move ahead. Then let's say an electron is jumping from one orbit to the next orbit. The energy difference between these orbits is given by this relation, 13.6 z square 1 by nl square minus 1 by nh square. nl corresponds to the orbit with the lower orbit number and h corresponds to the orbit higher orbit number. Now the previous one was in terms of energy, and if we have to know the wavelength of the photons released, we can use the Rydberg equation. 1 by lambda is equal to 1.1 into 10 to the power minus 5 into z square 1 by nl square minus 1 by nh square per centimeter. Note the unit as well. And now when you are removing the atom from n equal to 1, that is, this is the ionization energy. From ground state, you are removing the atom completely from the orbit. it is going to infinity. So delta energy required for that is known as ionization energy and is equal to 13.6 into Z square. One of the commonly tested topic in Bohr's atomic model is the hydrogen spectrum, and in that this formula, the maximum spectral lines, this is mostly asked in JEE Mains, and it is given by delta n plus 1 into delta n divided by 2. Delta n signifies the orbit number difference. Let's say the electron is jumping from 5 to 3, then the delta n is equal to 5 minus 3 equal to 2. Moving on, we have hydrogen spectrum, that is when electron is being jumping from the higher energy level to the lower energy level, it releases wavelength of certain regions, and if the electron is jumping from some orbit number to n is equal to 1, that is to the lowermost orbital number, then we call it as a Lyman series and it comes under UV region. If it is jumping from any other orbital number to n equal to 2, it comes under the Balmer series, and this is in the visible region. N equal to 3 Paschen, and it's in infrared. N equal to 4 bracket, it's in far infrared, and n equal to 5 it's fund, and it's also in infrared region. Note these regions, UV, visible, infrared, because this was tested in 2024 JEE Mains. So make sure you note all this: Lyman, Balmer, Paschen, bracket, fund, and which region it corresponds to. The next one is Heisenberg's uncertainty principle. In this principle, Heisenberg told that you cannot exactly predict both the position and momentum of the electron. There will be some certain errors, and delta x is the error in the position and delta p is the error in the momentum, and he gave this relation: delta x into delta p is greater than or equal to h by 4 pi. H is the Planck's constant, so if you substitute momentum as m into delta v, you will get this equation also. Even based on this, there was a question in 2024. The next one is de Broglie equation. De Broglie told that every particle has a wave-like behavior associated to it, and it has a wavelength, and so we call it as a de Broglie wavelength, and it is given by h by mv. M is the mass and v is the velocity. When an object with mass m is moving with the velocity v, it has a de Broglie wavelength of h by mv, and if you are writing mv in terms of kinetic energy, it will be h by under root of 2 mke, and the de Broglie wavelength for an electron moving in a potential difference of v is given by the relation under root of 150 by v, and this is in Armstrong's. Note that quantum numbers are numbers that describe the position of an electron in an atom. There are 4 quantum numbers. First one is the principal quantum number, which is denoted by n. This corresponds to the energy of the shell, and it can take values from 1, 2, 3 and so on. And next is the azimuthal quantum number, which is denoted by L. This gives the name of the subshell and the shape of the orbital. L can take values from 0, 1, 2, 3 up to n minus 1. When you can see here, L is 0, it corresponds to the s orbital, and maximum number of electrons which can be stored in the s orbital is 2. L is 1, orbital p, maximum number of electrons 6, 2, d 10 and 3f 14. These will help you when you are writing the electronic configuration, and when you see the recent previous year questions, writing electronic configuration is a most tested question. And other 2 quantum numbers are magnetic and spin quantum number. Magnetic quantum number is denoted by m, and it gives us the orientation of the orbital. It takes the value from minus L to plus L. Spin quantum number denotes the spin of the nucleus, and it takes the value plus or minus half. These are some formulas which are not usually tested, but still you have to remember these: total orbital angular momentum, total spin angular momentum, and spin only magnetic moment. Nodes, this is also an important concept. The number of nodes are usually tested. The total number of nodes in a particular given atom is n minus 1. N corresponds to the orbit number, and n minus 1 gives the total number of nodes. Total number of radial nodes is n minus 1 minus L. L is the azimuthal quantum number. Total number of angular nodes is L. Most commonly tested topic of quantum model is electronic configuration. You can see multiple questions in 2024 which has been asked from electronic configuration. I hope you know the Aufbau principle, wherein you will be filling the electrons based on the energy order. Lower energy levels has to be filled first: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. That is, subshells with minimum energy is filled first. And for writing the electronic configurations, if you know the atomic number of the noble gases, it will be very handy. That's why I have given here noble gases: helium, neon, argon, krypton, xenon, radon, argon, argon. And the atomic number is also given. There's a small trick like 2 plus 8 is 10, plus 8 is 18, and so on. Then you have to plus with 18, 18, 32, 32. With this, if you are remembering all these values, you can write the electronic configurations of any given element easily with the help of this. I hope you got this, and this was a quick revision of atomic structure. Next up, we have thermodynamics, and I have seen most of the students skipping thermodynamics and equilibrium, but there are multiple questions which can be solved just using formulas. Let's know how. Starting with the basic definitions in thermodynamics, that is state functions and path functions. State functions are functions which depend only upon the initial and final state. There are 7 state functions which you have to remember: pressure, volume, temperature, internal energy, enthalpy, entropy, free energy. And 3 path functions. Path functions depend upon initial and final state and also the path taken. And heat, work and heat capacity are 3 path functions which are there, and you have to note that delta H, delta S and delta G are neither state nor path functions. Note this. Then next is intensive and extensive properties. Intensive properties are the properties which are independent of the matter. It is the intrinsic property of the matters. Extensive properties depend upon the mass, that is, it is dependent on the matter. These are the examples of intensive and extensive. This is an exhaustive list, so make sure you take a note of all this. And in JEE Mains, it is highly probable that they will be asking these kind of examples as well. The next one is first law of thermodynamics. It is the energy conservation law, and in mathematical terms it is given as delta U, that is internal energy, is equal to Q plus W. Q is the heat and W is the work done. And the sign convention over here is heat, if it is absorbed by the system, it is positive, and it is released by the system, it is negative. Note that work done on the system is positive over here, and by the system is negative over here. In physics it is opposite. In chemistry we are doing this because we are more concerned on the system, and if the energy of the system is increasing, we'll take it as positive. That's what it is denoting here. Work done on the system is positive. And next, there are various thermodynamic processes. In isothermal is a process where the temperature is constant, dT is constant, and isochoric is volume constant. Isobaric, the pressure is constant. Adiabatic, the dQ is constant. Q, that heat is constant. There is no heat exchange happening. And when you plot the graph, PV graphs of this, you can see that P is a dP, that is in isobaric process, it's a constant line, horizontal line, and in isochoric process it is a vertical line. Isothermal and adiabatic, you can see a curve over there, and note that slope of adiabatic is higher than the slope of the isothermal. The next topic, the most important one, is the work done in various processes, and also we have to remember the work sign convention of work done. If it is done on the system, it is positive, and if it is done by the system, it is negative. Don't forget this. Many students used to confuse this. And next, the work done in irreversible process is given by minus of P external into delta V, and reversible it is given by the integration of minus P external dV going from V1 to V2, that is volume. In case of isobaric process, work done is equal to minus of P external V2 minus V1. In case of isothermal, reversible, it is given by the formula minus nRT ln of V2 by V1. If you are writing ln in terms of log, it will be ln is equal to 2.303 into log. So note that conversion also. And irreversible isothermal is minus P external into delta V. And in case of adiabatic, as I mentioned, in adiabatic, work done is directly equal to the delta U. This is from the first law because delta U is equal to W plus Q, and Q is 0 in adiabatic processes. And for an ideal gas, W is equal to NCV delta T. That is coming directly from delta U. Delta U is written as NCV delta T, and in regularly, usual formula for adiabatic work done is nR T2 minus T1 divided by gamma minus 1. Gamma is the adiabatic constant, and in terms of pressure, if you are writing, it is P2 V2 minus P1 V2 divided by gamma minus 1. And then in case of isochoric process, as there is no expansion or compression, work done is 0. And in cyclic processes, it is the area bounded by the curve in the PV diagram. In case of free expansion, expansion is against the vacuum, work done is equal to 0. Note this is also being tested in JEE Mains. Next topic is entropy. Entropy is the measure of degree of randomness or disorderness of the system. Mathematically, entropy of system is equal to Q reversible divided by temperature. For processes, generally entropy is given by two formulas, one in terms of CV and one in terms of CP. Note this. And for phase changes, delta system is given by delta enthalpy change divided by temperature. For fusion, delta H is enthalpy of fusion divided by the freezing point or melting point, and for vaporization, delta S of system is equal to enthalpy of vaporization divided by the boiling point. And the second law of thermodynamics states that entropy of universe is always increasing, that is, and delta S universe is greater than 0. The next one is enthalpy. Enthalpy is H and its relation with the internal energy E, and PV is given like H is equal to E plus PV. Gibbs free energy is the capacity of the system to do useful work. It measures that one. And G is equal to H minus TS. And when you write delta G is equal to delta H minus T delta S for a constant temperature thing. And at equilibrium, delta G is equal to 0, and if delta G is less than 0, if the process is spontaneous, it occurs naturally. That's what spontaneous means. And delta G is greater than 0, it is non-spontaneous process. You need an external factor for that process to take place. And finally, the third law states that at 0 Kelvin, the entropy of pure, perfect crystalline solid is taken as 0. Next up, we have electrochemistry, and we'll start with a quick trick, which goes like this. Anox, red cat, anode corresponds to oxidation and reduction takes place at cathode, and oil rig, oxidation is loss and reduction is gain of electrons. Next, we have some basics. Two types of cell which we'll be dealing in this chapter is galvanic cell and electrolytic cell. Galvanic cell is a cell where spontaneous redox reaction takes place, and electrolytic cell, non-spontaneous redox reaction takes place, and this is used in electrolysis. Next, we have cell representation. A cell is represented something like this, and the left part denotes the anode and the right part denotes the cathode. At anode, oxidation takes place and reduction takes place at cathode. And the two bars in the center represents the salt bridge. Next, we have the most important topic of this chapter, cell potential. For a standard cell, that is for 1 molar concentration and 1 bar pressure at temperature is equal to 298 Kelvin, cell potential is given as potential of cathode minus potential of anode. Note that these both are reduction potentials, but if it is a non-standard cell, we'll be using Nernst equation. E cell is equal to E naught cell minus 2.303 RT by NF log of Q. If we are taking some conditions, temperature is equal to 298 Kelvin, and substituting the values, you will be getting a simplified expression like this. And if you are wondering what is Q, let's say you have an equilibrium equation like that. Q is the concentration of the product raised to the stoichiometric coefficient divided by the concentration of the reactants raised to their respective stoichiometric coefficient. And at equilibrium, E cell is equal to 0 and Q is equal to the equilibrium constant. So you can deduce E naught cell as like this. From this, you will be able to find K equilibrium. Now we have a relationship between Gibbs free energy and electrochemistry, that is given by delta G naught is equal to minus NF E naught cell. E naught cell you can find using either Nernst equation or the standardized one, and from this you will be able to get K equivalent using the second equation. Delta G naught is equal to minus RT ln K equivalent. Note that F is the charge on 1 mole of electron, which is equal to 96,500 coulombs. Next up, we have electrolytic cells. Electrolytic cells are cells in which non-spontaneous redox reaction takes place, which results in the formation of some products. We will be using these cells for the electrolysis. Faraday gave two laws of electrolysis, and the first one says that the weight of the substance, that is mass deposited by electrolysis, is directly proportional to the charge passed. And when we simplify it, we'll get an expression like that. And the second law states that when you are passing same amount of charge to two different solutions, you will be getting mass deposited directly proportional to the equivalent weight. So you will have an expression like W1 by W2 is equal to E1 by E2 equal to Z1 by Z2. Next up, we have electrolytic conductance. In this, we have to know few terms like resistance. Resistance is given by rho L by A, where rho is the resistivity, A is the area of the conductance, and L is the distance between two electrodes. Conductivity is 1 by rho. Conductance, it is the reciprocal of the resistance and given by the relation G is equal to Ka by L. And the unit of this is ohm inverse or Siemens. Next up, we have molar conductivity, which denotes the conductance of solution containing 1 mole of electrolyte between the two electrodes, and it is given by the relation K into 1000 divided by the molarity. Note the units also. Next up, we have variations of molar conductivity. As you can see in the graph, as you dilute the solution, the molar conductance increases. That is, molar conductivity increases upon dilution. And for the strong electrolytes, you can have a linear relation. The relation is given below. And for the weak electrolytes, you don't have a linear relation. Next up, the final topic, we have Kohlrausch law, which states that limiting molar conductivity of any electrolyte is sum of equivalent ionic conductivities of the cation. Let's say you have a reaction like this, and you are about to find the molar conductivity of the molecule AXBY. You can see it is getting decomposed into cations and anions, and it is equal to the sum of the molar conductivities of cations and anions multiplied with the stoichiometric coefficients. What are the applications of this? The first one is to find the limiting molar conductivity of weak electrolytes, because from the graph you will be able to get the limiting molar conductivity of the strong electrolytes, but you cannot find the limiting molar conductivity of weak electrolytes. So you'll be using these relations. For example, you can see the limiting molar conductivity of a weak electrolyte HAC is found out using the molar conductivities of HCl, NaAC and NaCl. These things we'll be getting from the graph directly. Next up, we have next application as to determine degrees of dissociation. Degree of dissociation is given by molar conductivity divided by the limiting molar conductivity. Next up, we have chemical kinetics, and I hope you are enjoying this video. Subscribe to our channel for more such awesome contents. Let's start this with the rate of a reaction. Let's say there is a reaction given by this. You will be writing rate of reaction either in terms of rate of disappearance of reactants or appearance of the product, and it is given by the relation minus dA by dt or minus dB by dt for in case of disappearance, and dC by dt and dD by dt in case of appearance. Minus sign occurs because it is disappearing, and a relationship between individual rates can be noted here. Stoichiometric coefficients also get involved, so note that. Next up, we have rate law. It's just an expression that relates the rate with the concentrations of the reactants. Let's say there is an equation given by A plus B giving you C plus D, and the rate is directly proportional to concentration of A raised to the power X and concentration of B raised to the power Y. X and Y may or may not be stoichiometric coefficients, and K is the rate constant over there, and it depends only on the temperature. Now, order of the reaction, order is just the sum of the exponents in the rate law. Over here it is X plus Y. Next up, we have integrated rate law method. Suppose you have a reaction, A is giving some products, then you can write rate as rate is equal to K concentration of A to the power N. N can be anything depending on the order. We'll be solving this differential equations for different order of reactions and getting various analysis. So starting with zero order, you can see that concentration of A to the power 0 is 1, so it is a constant. And when you do these integration, you will get the relationship between concentration of A with respect to time. So concentration of A at any time is equal to initial concentration minus KT. This is an important relation. Next up, we have first order reaction, and when you do all the integrations, you will get the final expression as concentration of A is equal to initial concentration multiplied by e to the power minus KT. And next is the concept of half-life. It tells us that the time taken for initial concentration A to become half of it. In the concentration expressions which we got earlier, we'll be substituting A is equal to A naught by 2, and while doing the analysis you will get T half as A naught by 2K for zero order reaction and a constant value for first order, that is ln2 by K. ln2 ka value is 0.693. This is the summary of zero and first order reaction. These are some logarithmic values you should know to solve few numericals in JEE Mains. Next, we have graphical analysis, and in graphical analysis, first up we have rate versus concentration. You will be plotting a graph between rate and concentration. When you plot for the zero order reaction, you will get a straight line, it's constant, and and for first order it is linearly increasing. Next we have concentration versus time, how concentration varies with respect to time. And for zero order you can see that initially it is starting and linearly it is decreasing to 0, and for first order you can see it is exponentially decreasing. When you take logarithmic and plot a graph between log of a with respect to time, you will get a graph similar to the zero order. Next we have half-life versus initial concentration, and in zero order reaction the half-life depends on the initial concentration directly, so you'll have a straight line graph like that. In first order reaction, as you know, the half-life is a constant, it does not depend on the initial concentration, so it's a constant graph. In case of gaseous reactants, progress is monitored by pressure, and as we did in terms of concentration, here you will be doing in terms of pressure. P at any moment is equal to P naught e to the power minus kT. This is very similar to the first order reaction analysis. Then we have Arrhenius theory. This states the variation of rate constant with respect to temperature given by K is equal to A is the Arrhenius constant, e to the power minus EA RT. You can find that EA is the activation energy, R is the gas constant, and temperature is in Kelvin. Note that many students make this mistake. Temperature should be substituted in Kelvin. Next, let's say you have two different temperatures T1 and T2, and we have two different rate constant K1 and K2. We'll find a relationship between K1, K2 and T1 and T2. When we take ln and do analysis, we'll get a final expression similar to this. I hope you got this, and if you're enjoying, please let me know that how this video is going so far in the comment section, so that I'll be creating more videos for the upcoming sessions of JEE. Moving on, we have equilibrium. By equilibrium, what we mean is rate of forward reaction is equal to the rate of backward reaction. This is represented in graph like this. In this, we have law of mass action, which tells us that if there is an equilibrium equation like this, the rate of forward reaction is directly proportional to the concentration of the reactants raised to the respective stoichiometric coefficient. Similarly, rate of backward reaction is directly proportional to the concentration of the products raised to the stoichiometric coefficients. Kf and Kb are the rate constants, the forward rate constants and backward rate constants. At equilibrium, rate of forward is equal to the rate of backward. So when we equate it, we get a special quantity known as equilibrium constant Kc. Equilibrium constant is defined as Kf by Kb and is equal to the concentration of the products raised to their respective stoichiometric coefficients divided by the concentrations of the reactants raised to their stoichiometric coefficients. This is an easy question from equilibrium. People who skip this chapter would not able to do this, so please make sure you do this question. Next, moving on, we have gas reactions, and this is equilibrium constant in terms of pressure. Earlier it was in terms of concentration. Similarly, in terms of pressure, if you are writing, we have Kp given like this, and the relationship between Kp and Kc is usually tested in JEE Mains, and it is very important. It is given by Kp is equal to Kc multiplied by RT raised to the power delta Ng. Delta Ng is the difference between the moles of the gaseous products minus moles of the gaseous reactants. In this question, you can see there is CO plus half O2 in equilibrium with CO2, and delta Ng is given as 1 minus 1 plus half. 1 plus half corresponds to the reactants and 1 corresponds to the products. This is an easy question, and it tests us the relationship between Kp and Kc. Moving on, we have characteristics of equilibrium constant. First one is when the reaction is reversed, that is when products is written as reactants and the reactants become the product. Equilibrium constant of the new reaction is 1 by K equilibrium. When you are multiplying the entire equilibrium reaction with n, the equilibrium constant is raised to the power n. And finally, when you are adding two or more reactions with equilibrium constant K1 and K2, the equilibrium constant of the new reaction is K1 into K2. This can be applied in a recent JEE Main question 2024. Make sure you do this. Moving on, we have degree of dissociation. Degree of dissociation is defined as moles dissociated divided by the initial moles. You can apply this in the following example. Let's say the following reaction, 2Hi giving in equilibrium with H2 and I2 has the degree of dissociation as alpha. So at T equal to 0, that is initially, let's say X moles of Hi is present, and as time passes and we reach equilibrium, at time equal to T equilibrium, we have moles of Hi given by X minus 2 alpha. 2 is the stoichiometric coefficient of Hi. It is coming because alpha is the degree of dissociation, and alpha are the concentrations of H2 and I2. From this, you can write the equilibrium constant of this reaction as H2 concentration, I2 concentration divided by Hi concentration raised to the power 2. 2 is the stoichiometric coefficient. When you are finding it, you will find it as alpha square divided by x minus 2 alpha whole square. Even based on this, questions are being asked. The final topic is Le-Chatelain's principle. It gives us information that if you disturb the equilibrium of the system, then system undergoes a change and brings the system back to equilibrium. And let's say you have an equilibrium reaction like this, and you are increasing the reactance. What happens? The equilibrium shifts towards the product side, that is forward reactions happen. And if you are increasing the amount of products, to bring it back to the equilibrium, then the equilibrium shifts back, that is the backward reaction occurs and it comes back to equilibrium. Please note that addition of solid or liquid does not affect the equilibrium. This was tested in recent JEE Main question. Next up, you have increasing the pressure. If the delta Ng is greater than 0, then the reaction moves backward. If the delta Ng is less than 0, the reaction moves forward. If delta Ng is equal to 0, there is no shift in equilibrium and the equilibrium remains. Then you have addition of inert gases. If you are adding inert gases at constant volume, there is no shift in equilibrium. But if you are adding in constant pressure, according to delta Ng, you can see the effect over there. Next up, we have ionic equilibrium, and the first one is pH calculations. pH is equal to minus of log of concentration of H plus ions, and pOH is negative log of OH minus concentration. pH plus pOH is equal to 14 and at 25 degrees Celsius. H2O, when it is decomposing into H plus and OH minus, in this, if you are writing the equilibrium constant K equilibrium, you will get an expression like that. And now when you are multiplying K equilibrium with concentration of H2O in liquid, you get H plus concentration multiplied by OH minus concentration. And here the concentration of H2O liquid is 55.55. The term in the LHS, K equilibrium multiplied by 55.55, is termed as the ionic product of water, KW. KW is equal to K equivalent multiplied by 55.55. This was once tested in JEE. Next up, we have salt hydrolysis. In this, we will be finding the pH of the salt solution formed from the different combinations of acids and bases. First, we have weak acid plus strong base, then we have strong acid plus weak base, and then is weak acid plus weak base. What happens is the weaker component ions will get hydrolyzed. The first one is weak acid, so it is termed as the anionic hydrolysis. The second one is cationic hydrolysis, and then was anionic and cationic hydrolysis. pH in first case is half into pKw plus pKa plus log C. In the second case, pH is given by this relation, and in the third case, pH is given by pH is equal to half into pKw plus pKa minus pKb. Now when you are writing the KH is equal to Kw by Ka in first case. In second case, Ka is replaced by Kb, as it is weak base. You can relate like that. And in third case, it is both Ka and Kb. KH is equal to Kw by Ka Kb. And degree of hydrolysis also you can find it. In first case, it is under root of KH by C. In second case also it's the same, and in the final case it is just under root of KH. And for strong acids and strong bases, pH is always 7. Next, we have buffer solutions. These are solutions which resist pH change on addition of a little bit of acid or salt. We have two buffer solutions. One is acidic buffer, wherein we have weak acid plus salt of weak acid plus strong base, and the pH is given by this relation, pKa plus log of salt concentration divided by acid concentration. Next, we have basic buffer, which is combination of weak base and a salt of weak base plus strong acid. The pOH of the solution is given by the relation pKb plus log of salt concentration divided by the base concentration. Next, we have solubility and solubility product. This is mostly tested in JEE Mains. Solubility is denoted by S and the unit is moles per liter. Let's say you have a sparingly soluble salt in the equilibrium reaction like this. Ax plus By is the salt, and initially you have C concentration, and at equilibrium, due to its solubility S, you are having a relation like this. The moles of A and B ions are given here by Xs and Ys. So when you write the KSP, the solubility product is written in terms of concentration of the products raised to their stoichiometric coefficients. Here Xs raised to X and Ys raised to Y. X and Y are stoichiometric coefficients over here. Based on this, there are multiple questions being tested in JEE Mains. Make sure you note this. Next, we have indicators for acids and base titration. This is a conceptual topic, and if you know all these, which indicator is used for which cases, then you can solve the questions very easily. Please make sure you note this. And with that, we conclude the entire physical chemistry, and I hope it was a great video. Let me know in the comments which video you want next, and subscribe and stay tuned. All the best.